Hello and welcome back. Let's talk about some areas. So, let's say we want to find the area under a curve. Let's say this curve is x squared. Y equals x squared, of course. I'll put my x and y. So we want to find the area between 0 and 2. Just going to estimate where 2 is. We'll write our 1 here. Well, what we can do, a simple approach would be, let's split our curve into two areas, and one from 0 to 1, one from 1 to 2. Let's find the area of these two rectangles. Well, first we need to find the height of each rectangle, so we can represent both of these heights in one equation. We'll call the x value xk. We call our left endpoint A, our right endpoint B. A is 0, B is 2. So our first we need to find the size of the base of these rectangles, and so the base we call delta x, and that's just going to be b minus a divided by the number of rectangles we have, so 2 minus 0 divided by 2, which is just 1, which makes this very easy. You're going to see why I chose this function and everything very soon. And so what we can do is we can say xk, we're finding the right side as the height. We could use the left side if we wanted to, but that would just get rid of this rectangle. That wouldn't be any fun. Let's use the right endpoint. Well, our xk is going to be, it always starts at 1. So we can say it's x in terms of k is a, which is just 0, plus k is 1 at the start, k times delta x. So when k is 2, it's 2 because delta x is just 1, so we don't have to put 1 there. So xk just equals k. That makes it very easy. That means our function of xk is just k squared because our function is x squared. So we replace x with our xk. So function of xk is k squared. Now, if you remember some notation from our past knowledge from some math, regular math, not calculus classes, we might remember that we can actually express these as a sum. So we're going to use the sum as I said, k starts at 1, and we'll say it goes to n of f of xk times delta x. And so this is our general formula for finding the area under a curve. So you'll notice that k goes from 1 and we have two rectangles. So in this case, we have the sum from k equals 1 to 2 of f of xk is k squared times delta x is 1. So what's this? This is 1 squared plus 2 squared. This is just 3. Very easy stuff. And, oh, sorry, 2 squared is not 2. That's actually 5. And this makes sense because this point here is going to be 4. This point here, if we bring it across, this is going to be at 4. I shouldn't have drawn that there. Our point here is going to be at 1. 1 times 1 plus 4 times 1 is 5. Very good. What if we wanted to make this more accurate? Well, we'd split it into 4 rectangles. Let's do that. Four rectangles. So that'd be the sum from k equals 1 to 4. Our delta x would then become 1/2. Let's see here, k squared times 1/2, which is the same as sum from k equals 1 4. Since we have 4 rectangles, 4, we can bring the 1/2 out front of k squared. That's just 1/2 times 1 squared plus 2 squared plus 3 squared plus 4 squared. And that is 1/2 times 1 plus 4 plus 9 plus 16. That is 5 plus 25, 30 divided by 2 is 15. I believe. Sorry, no. Our 1/2 is going to be in the k, so it's 1/2 squared. 1/2 k squared, so it's 1/4. So it's actually 1/4. So this would be 7.5, 15/2. So we're getting more accurate as we keep going. If we wanted to split these into even smaller rectangles, we could, but let's make an infinite number of rectangles with a size approaching 0. What's this? This is our original sum, just in terms of k and n. Let's replace delta x with what we know it is, b minus a over n. And let's take the limit as n, because n is the number of rectangles. Let's take the limit as that goes to infinity. And that all of a sudden becomes very complicated. So this is actually how we represent it. The integral, we call it, from a to b of f of x with respect to x. And respect to x means that we're taking very, very, very small x terms. As we remember, dy over dx, that was the rise over the run. Our rise was a very small y. Our run was a very small x. And that's how we found the slope. And our f of x is the height of the function at that point x with a very, very small size dx. So let's just evaluate this integral. Well, that's going to be the integral from a is 0 to 2 of x squared dx. This is, well, first I'll have to introduce the fundamental theorem of calculus. The first one, there's a lot of them actually, which says that the integral from a to b of f of x dx equals f of b minus f of a. And so what is this? What is this capital F? This capital F is the antiderivative of our function x. So let's look at it with this again. Our elongated s, sum, x squared dx. The antiderivative of x squared is x to the 3 over 3. And then we're going to use this to say evaluated from x equals 2 to 0. So we plug in 2, we plug in 0. We know that if we plug in 0, this is just going to be 0. So this is just 2 cubed over 3, which is 8 over 3. Very cool stuff. So that's your integrals. Now, let's get into the last part of this video, and that is, what if we had this? What if we had y equals x, but we also had y equals x squared, and we wanted to find this area? Well, first, we know that y equals x squared and y equals x will intersect at 1, 1. Which is where x equals 1. We can do that using some simple algebra. We let y equal y, x squared equals x squared minus x equals 0 equals 0 and 1. So this is our other intersection point, 0 So let's find this little area here like this. Well, what is that? Well, we know we've got two areas that we can find using our fundamental theorem of calculus that I just introduced. So we've got this big area from here all the way down to the x-axis. We've got this little area from here all the way down to the x-axis. So how can we find this little area here? Well, that's just going to be the big area minus the little area, because that will leave us with this. So that is the area under y equals x from 0 to 1 minus the area from 0 to 1 of x squared. And so that is our area there. Let's evaluate this right quick. This is x squared, evaluate x squared over 2, 1 over 2 x squared, evaluated from 0 to 1, minus x cubed over 3, evaluated from 0 to 1. This becomes 1 over 2, because when we plug in 0, we get 0. When we plug into 0 of this, we get the same thing. 1 cubed over 3, it's 1 over 3. 1/2 minus 1/3, let's do some quick algebra. This is 3 over 6 minus 2 over 6. This is 1/6. So 1/6 is our area right here. That is wonderful. And I believe that is our second last video on Calc 1. The last thing we have to talk about is evaluating complicated integrals such as, let's say, give you a little look into what the next video is going to be. Maybe we'll do this. No, I mean, that's a pretty simple one, but we'll see how it looks in the next video. Thanks for watching. I hope this helped. Hope you guys are all doing well. If you're watching this video, you might be approaching a Calc 1 final exam. I hope that goes very well for everybody. I hope the next video also helps. But thanks for watching. I'll catch you in the next one.